So let me start with a short story. You know, this stream was planned a long time ago. And of course, nowadays we are all overflown with digital content, with streams, with online conference, and that's it. So I hope that there is anyone there in this stream. So I will talk about one chapter of the upcoming Haskell in-depth book. It will be published this fall, I promise. I'm writing it for a very long time, but it will be finished eventually. And I will use, for the source of this stream, I will use chapter 11, which is called Type System Advances. And this table of content here is a little bit outdated. In fact, while I was writing this chapter, I decided that one chapter is not enough for such important thing for Haskell. So now we have chapter 11 on type system advances, and then I also have chapter 13, which is called more about types. And the reason is that, well, I have too much content for one chapter, but I also have decided to split it into two parts. So the first part is what do we have, which tools do we have in Haskell to do type level programming, to work with types. And this will be material of this stream, the material of chapter 11. And then what can be done using all those tools to do actual type level programming. So this will be material of chapter 13. So I will give you an introduction to the type system, to the tools which I use at type level. And then if you like it, you will buy this book and then you will use it. All right, for all of you, if you are interested, there is a promo code tweet40. So I will mention it one more time. Tweet40. You can use it to get 40% of discount for this book. So if you want. Okay, so chapter 11 of the upcoming Haskell in-depth book. And now I will switch the scene here. I have my own setup, and then I will try to look at the chat from time to time. So please, if you have any questions, write them. I will try to answer them just as they're coming. I think it will take about an hour to go over this stream. Okay. So I'll tell you, yeah, and I have to say that if you want to follow the code, you can do that with this link on GitHub. I have a repo for this tutorial, github.com here, Bravit Hid Examples Chapter 11. There is a repo for hid examples. It's the repo with all the examples from the book. It is open, it is public, so you can look there if you're interested. But this is an excerpt from that repo, only examples, a little bit tweaked examples from chapter 11. And when I say tweaked, I mean this. I have my own demo program which executes GHCI, and it shows some code, it shows examples. I'm not very good at speed typing, actually. So that's why in this tutorial, I will not use it almost. But I've prepared everything in advance. So I will show you examples as if I'm typing it like as a rocket very quickly. but actually they are programmed, so they are comments in the files. You can see in these files you will be able to see some comments, and they are actually executed in the GHCI. Okay. So if there are no questions, and it looks like we have no any questions now, so okay, then let's start with the introduction, right? Okay, so this is tutorial about type system, about types as we can use in type level programming. But of course, we all know that it is possible to use Haskell just as a calculator without thinking about types at all. And this is a very interesting feature of Haskell. So in fact, we don't need types quite often. So for example, we have this function. We don't know anything about types. We have no types mentioned here. It's just some function for, well, for converting Fahrenheit degrees to Celsius. And we can use it as follows. So we can just call it this function with some argument. And here we have a result and another argument and another result. So no types at this point. But then, of course, this function and every other function in Haskell, they have a type. So we never mentioned it, but it was inferred. So this is type checking, type inference. Whenever we compile our code, we always have a type. And in this case, this is a function which this type. It's from type A to type A when A is constrained by some type class fractional. So this type was inferred thanks to the operations we use over the variable in the code. So we have division here, we have multiplication. So that's why it is fractional. Fractional mainly, so it's not general number, it's a fractional because we have used division there. All right. And we can also ask for a type of a value. Here, for example, if we have a function with an argument, then we can ask for a value. And this value is also fractional. So it's of type A, which is constrained by the fractional type class. So all this information was inferred somehow. And thanks to this type inference, we can use this function with many different types. For example, we can use data ratio. Unfortunately, this module is not very, it looks like it is not very popular, but in Haskell we have ratios and they're very convenient for many problems. So we can use this function with rationals. So this is 100-third. And it also works. So now it's not a floating point number, it's ratio, but this function works for ratios either. So this is the result of type checking and type inference, and one of the simplest things in Haskell type system. So we can use one function polymorphically with different types, like integers, ratios, that's it. Okay. Let's go back here to the code, and we can also fix particular types. Well, sometimes we do want to write polymorphic functions. Sometimes we don't. Sometimes we want to have concrete specific types, and in that case, we can write them right as a type annotation in our code, and we say, well, this function is a function from double to double. And if we look at it now, so this function works over doubles. And although we've used 32, which is, well, it looks like an integer, but thanks to the properties of GHCI, it is considered as a double value. And we also have a result of type double. Okay. So in Haskell, as we look at it now, we have terms, and we have types. So terms are variables, our literals, numbers, and types are double, ratio, integer, and all others. Okay. But the next thing which is very interested in Haskell, and this is something, well, we have types and terms in many programming languages nowadays, like we have them in Java, we have them in C# and many other programming languages. But besides them, in Haskell, we have also kinds. So it's a tool to classify types, and this is one of the most important tools for doing type-level programming. So what can we do with that? So we can ask for a kind of integer. Remember, integer was a type. So we can ask for it. And it's something. We say star. The kind is star. So we can ask for the kind of int type, and it is also a star. We can ask for a kind of maybe, and it's not a star, but it's a star to star instead. So we know that maybe is not a real type, it's actually a type constructor, and we have to supply another type to it in order to get type. So we can do that. And for example, maybe int, it's a type, and its kind is star. And now this star thing is a little bit outdated. We try not to use it anymore in modern day Haskell. Instead, we are using another word, which is type. So in order to use it in GHCI, we have to set this GHCI extension, GHC extension, no star is type. So once this extension is enabled, we don't use star to denote this kind type. By the way, we can use it for other things, as we'll see shortly. And now, if we ask for the kind of integer, then it will be type. So this is should be clear. So, well, integer is a type, and bool is also a type. And maybe is type to type, and we look at it as a function which takes type as an argument and gives us type as a result back. Okay. Either, we know that either has two arguments, type for left, type for right. And well, it has two type arguments, and we can see it here. So it's a function, it takes two type arguments and gives us type either int, bool, for example. And maybe int, if we apply this type level function. So for us, maybe and either, they are simplest type level functions. So they operate over types. So kind of maybe int is type. So this is fully applied function, which works on type level. Okay, remember we had fractional. Fractional is definitely, it's not a type, it's a type class, but we can also look at its kind. So what's the kind of fractional? And it turns out that its kind is type to constraint. So fractional is also a function over types. It takes a type as an argument, but it gives us back a constraint. And if we apply some type, we have a constraint as a result. So constraint is another kind. We have types and we have also constraints. These are two different kinds which we can use in nowadays Haskell. And monad, another type class, it also has some kind, and this kind, we can see it is a function which takes an argument which is a type level function. For example, maybe can be an argument to monad because it is from type to type. and many other types cannot be an argument to monad. Okay, so kind maybe is type to type. We know that, so we can put this maybe into a monad, and we can get corresponding constraint. All right. So we cannot ask for kind of monad int. Why? Because we have kind checker. Just as we have a type checker in Haskell, we also have kind checker. And monad expects a function type to type as an argument, and int is not like that. So, well, we say, okay, this function is not, this type is not appropriate as an argument. So it's not about some ideology that integer cannot be turned into a monad. It's simply about kinds. So int has just wrong kind to be an argument to a monad. Okay, but now let's look at a little bit different thing. So there can be something like that. So what if we have maybe a, not maybe in, but maybe a, and we want to look at the kind of this type? Well, we have a type, we have an error. So this type variable a is not in scope. So a is unknown to a compiler at this point. So that's why we cannot ask for a kind. But what we can actually do, we can introduce this type variable and ask for a kind. So we can do that with one of the extensions. For example, there are several extensions which enable this functionality. For example, explicit for all extension. So if we set it, so then we can introduce this maybe this a variable with the following syntax. So we can write for all a maybe a, and now it is known to a compiler, and it says, well, this type has kind type. Okay, so we can use types which are available from the library. We can introduce our own type variables and then use with these kind calculations. And we can also ask for a kind for a general monad parameterized with some type m. Well, and it is a constraint. We all know that monad m is some sort of constraint which is quite often used. And the final question in this introduction, this short introduction, is the first file of this tutorial. So can we classify kinds? So we have types, we have constraints as kinds. And in order to get access to these names, type and constraint, I am doing this import, and then I can ask for a type of type. Well, we have an error because it's not a data constructor, and we can ask for type for data constructors exclusively. But what if we ask for a kind? And this is one of the most interesting results here. So, well, type has also kind, and this kind is also type. So types are kinds actually here in Haskell. So this is a property of type system. So every kinds are classified, and we use the same kinds for the classification. So types are types. And constraint, well, it is also type. Okay, so now we have terms, types, we have kinds, and kinds are also types. This is types are types. This is exactly this. Okay, so and now let's get to more interesting stuff. So we have terms, types, and kinds, and what we can do with them. I'm going to the next file. I'm following this my plan. And in this plan, I have, So phantom types. I will open the file. Here is it. Let's look here. So this is quite an old technique. So we can use type variables without actually referring to them in the type definition itself. So I will show you several examples about temperatures. Temperatures as we can use in Haskell programs. So here I have a type for storing temperatures, and every temperature is stored as a double value here. And let's look at this definition. So type temp has an argument. It's some type variable which is called unit, but it is never used on the right-hand side. Just for convenience, I'm deriving here several type classes. For example, num, so it's a number. So I want to operate over this double, just as if it's a double number. The temperature is a double number. This deriving requires this extension, generalized type deriving. By the way, chapter 12 is devoted to many sorts of meta programming in Haskell, and it starts with the ways to derive instances. It is not yet published, but it will be soon, I hope. It is already written. So it started with a discussion how we can derive types and type instances in Haskell. So we've derived these three type classes. And then we also have these two empty declarations. So we need these types only for referring to types. And we mean that F is Fahrenheit degrees and C is for Celsius degrees. And these types have no values. They are used at type level. This is the first feature of type level programming, actually. So these data types, they exist only at the level of types. We have no representatives for these types at the level of terms. So they exist on type level exclusively. And this is how we can use them. For example, here you can see two values. One is degrees in Fahrenheit degrees, and another one is Celsius degrees. Just two almost random values. Okay, so let's load here with my demo GHCI, this program. Okay. Is it possible to do something like that? So we want to subtract one temperature from another. These two values, they have different types. The first one is temp F, the second one is temp C. So types are different, and we clearly have a type error. So why do we use types here, this F and C? Well, we want to control our values. While both values are double numbers, we want them to be of different types. So that's why we use these empty types here. So, well, that's an error. It's impossible to do that. But of course, if two values have the same type, we can compute the result. So here it's 0. So these two variables, it's just actually one variable, so it has some type, so we can do operations over it. So it works. All right. But of course, we can write conversion function. And just as we did it before, we can write it this way. It turns Fahrenheit degrees to Celsius degrees. And we can look back to the GHCI and see, well, now it is possible. So we've converted it to the same type temp C, and now we can do subtraction and we can get a result. Okay. Unfortunately, with these phantom types, we can get something like that. We can write nonsense definitions, and it works. So nonsense, well, tembool, what does it mean, tembool? We don't have such scale. And remember, this bool type, it is never used in the right-hand side of the type declaration. So, well, just nonsense. But with these phantom types, we don't get control. Note, we can express an idea of having different scales for degrees, but we cannot check that user follows this idea correctly. So of course, it can be used in the right way, but it also can be used in an incorrect way, just as here. Okay, so this is an idea of phantom types is very old. It is still used quite often in modern Haskell libraries, but it's outdated. So, well, we're not supposed to use it now. So there's no control at the level of types. We can express our ideas, but we cannot control them. Let's look at something more interesting here. I will open another file. Proxies. This is an also an ancient technique. And with this technique, we will use this module. It comes from base package. We don't have to load something specifically for it. And here, this data type, it is already defined in this module, data proxy. And you see that it uses phantom type in its definition. So we have a value now, which is called proxy. And the type T is not used in that value. And this declaration means that we use this type T only to, this proxy type only to refer to some type at the level of types. Again, there is only one value for any such type. And I will use it as follows. So I have a class for unit names here with only one function, unit name. And this function takes an argument of type proxy u, and it gets us back a string value. So I want to get a string for unit name. Is it either Celsius or Fahrenheit or whatever? And here you can see two instances. So this proxy type here is used to specify the particular type. If it's C, then the result is string C. If it's F, then the result is F. So let's look at this in GHCI. Once again, this demo program. And I'm trying to create these proxies. So this is how I'm doing that. To call this unit name function, I have to give you a proxy, give a proxy as an argument. But what is proxy? Proxy is something unknown unless we specify a particular type. So if it's proxy F, then the result will be F. Okay. If it's proxy C, then the result is C. So this value proxy is used to give us additional information about particular type. And then we can use it here. Okay. So very simple type class, very simple instances, and we can use them to implement this nice show instance for temperature. So look here at this instance. So this instance for unit name for the given temperature. So now we have temperature as an argument to this type. And we refer to another instance with proxy. And in this proxy, we give a particular argument. So now it's a unit which comes from the unit type from the head of this instance. So unit name for a temperature in Celsius will be C. For Fahrenheit, it will be Fahrenheit. Okay. So let's look at how it works. So for example, paper burning, it's 4510, and let's look here. So we know that the type is temp F. So that's why we've got here. So we show the double value, we show this degree symbol, and then we refer to the particular unit of this type. And then this function is also called, and then we get back and it was F. As if it was F, we go to this instance. So we use this instance resolution to get to the right letter F here. Okay. By the way, there is one comment in the tweet chat. I only know HTML. Well, I know HTML either, but yeah, this is about Haskell. And by the way, I'm sorry if I did not say that in the very beginning. All Haskell in Dev book is by no means a book for Haskell beginners. So no Haskell beginners here. It's this book is advertised as second level book. So, well, I'm sorry, but it may be completely nonsense for everyone without Haskell background first. Okay, so this proxy technique is used here to do something, well, very real, to get show instances. Okay, and yeah, and I'll go further. I'll go further here. So let's look at this function. And these proxies, they are often used together with the scope type variables JC extension. And this extension is very, very simple. So let's look here. So we have some type which is polymorphic, which refers to the type variable u. And in order to call this unit name function, we want to refer to that u. So this scope type variable extension gives you two things. It allows you to write for all u in types first, and then it allows you to refer to this u here. So in some sense, it connects your terms with your types. So you have type u in type variable u in type annotation, type signature, and then you refer to it here in the type signature right inside your body. So this is scope type variables. It gives you an ability to refer to the type variables used in type signature. So we have this type, we construct proxy, and we refer to it. And well, it works. It works here. And all this instance resolution works at this moment. So JC finds a specific instance for us. And for absolute zero, it works either. Okay. I will stop with this example. I will go further. And I have type applications. So another comment or question in chat: hasn't proxy become obsolete after introduction of visible type applications? Well, no. These techniques that are used for closed things, but they are quite different. And I will give you this difference in a second. So let's get to the type applications. And this will be another example here. Right, and I will run it here. So very short introduction to type applications. Let's look to the GHCI. So remember, proxy was one way to deliver information about types. Visible type applications is another way to do that. So remember plain old read function. If we ask for its type, it will be read A with this constraint from string to A. So this function takes a string and converts it, parse it to some value of some unknown type. So in order to use this function, we have to specify it somehow. So specify this type. Why? Because this function has one implicit argument. We can ask for this argument for printing it explicitly, like this. And if I ask for the type of the read function, you will see it. So here for all A, this is implicit type argument. And we can use this function differently. First, we can specify a returned type. So in this case, GHC knows that, well, we need an integer, and the result is an integer. But here we have another application, type applications, which allows us to give this type explicitly. So just a syntax extension, technically. So we can say, well, please use this read function with type int. This @int means type applied. So basically, we give this int type for the first implicit argument here. So the argument was implicit, it was a type, and we give it this value. And then it also works. So you see that this is another way to deliver type information. Proxy was the first one, type application is another one. And now to this question, hasn't proxy become obsolete? Yeah, by the way, the type is of course int because we've specified it. Well, let's get back to the temperature example. And in that example, we'll see that it's not that simple. It's not about some extension being obsolete. So here, in this example, I have several new extensions. So this is type application, which I am talking about right now. And unfortunately, in many cases, when we want to use this type application, we also want to use this not very nice extension, which is called allow ambiguous types. So that's why I don't like type applications. Why we need that? Well, the answer is quite simple. So let's look at the new version of the unit name type class. Now it looks much nicer than before with proxies. Of course, we don't have to specify these proxies explicitly. Instead, we have this type U implicit in the unit name. And if we have type C in a context, then the result is C. If we have F, then the result is F. So this looks much simpler. But the problem is that whenever we have this unit name, we never know an exact type before we call this function and before we specify this explicitly, this type explicitly. So that's the difference. When we had proxies, we never need this allow ambiguous types extension because we knew exactly that this type is specified here. But now, what is unit name? Well, we don't know. We cannot infer type for it. Maybe it will be known sometime when we call it. Well, maybe not. So when we define these functions, we cannot see an error, but we may see an error later. So that's why it's not a very good thing. So, well, it may be convenient, but it may be also dangerous, because we can make an error here and our types will not be checked here at this point when we define them. All right, so that's the difference. But of course, this is a nice code and we can use it. So we have these two instances, and we also can define another instance, which is quite interesting. To remember the temp type. Temp type had an argument. So temp has different kind. C and F, they are types. And temp is not type, it's type to type. Remember, it has temp unit is equals to something. But we still can define this type class for this type, temp, for this type constructor, thanks to the polykines extension. With this extension enabled, and I had it enabled in the very beginning, we can use this type variable U in type class definition for any kinds. So polymorphism means we can use it for kinds type, we can use it for kinds type to type, we can use it for kind type to type to type, etc. So, well, that's polymorphic kinds, kind polymorphism here in its simplest form. And you see that, like in this tutorial, I'm trying to get the simplest examples to introduce all those extensions. Okay, so kinds polymorphism is an ability to use types of different kinds for standing for one type variable, like here. All right, let's load this into GHCI. It's temperatures example. So we have to set this extension here, and then we can use visible type applications to call for the unit name function. Well, it's C here, and it works. So we know that we have specified this type here, using visible type application, and we've got the right result coming from this instance. All right. And we can also define the same things as before. We can define show instance, and we can use this visible type application just as before. So this is the same code as with proxies, but a little bit nicer. So, well, it's more convenient with this extension. We have no more things with proxies, but still proxies are very often used. So it's still a very important tool in Haskell. So, and of course we can check if it works, and well, it works. So we can ask for the unit, and it works. Okay, and the last simple thing here, type operators. I will not talk much about them. So this is a pretty technical, pretty syntactical thing. So type operators extension is used for defining types like this one. So we can use plus in type, we can use multiplication in type. By the way, this star is available because we have this no star is type extension. So now we can use it in type, for example. So if you want, you can look at this example by yourself. I will not go further. So I personally am not very fond of these operators in types, because we can get some not very easy readable expressions and types, but still, well, sometimes we can use them for good things. So syntactical thing, use operators at the level of types to construct something. These type operators, they are often abused when people try to implement different mathematical things over types, and the code becomes very difficult to read. So, but still, it is possible, right? And now, more interesting stuff, data kinds. Let's look at the temperature example again. And I will run it now. Here we are. And now it's a perfect new world. It's quite old, and we have more extensions here, as you can see. So data kinds were implemented like, I think 6, maybe 7 years ago. So it's quite a mature tool right now. But now the idea is to control types. Remember, we had temp bool type with phantom types, which is not very good. So now we define a new data type for temp units. Now temp units are F and C. And with data kinds extension, temp units becomes a new kind, and F and C become new types. So we promote data constructors to type constructors, and type constructors to kind constructors. So before we had only two kinds, constraint and type. Now we have another new kind, temp units. And we can use it using, we can specify an expected kind using kind signatures JSC extension. So now we say, well, this U is not any type. It's a type of this particular kind temp units. And we don't allow anything else. We don't allow bool, we don't allow whatever. So let's look at how it works. So of course we have to set all these extensions in JCI either. So what's the type of F? Well, it's temp units. It's data constructor and it has a type. So what's the kind of F? Well, it's temp units. So temp units is a new kind. So what's the kind of temp units? Well, it's a type. We remember the type is type, so it's also a type. And we can ask, just as before, we can ask for such expressions. And of course it works. And I have show instance, by the way. And of course, it is also checked just as before. We have type error. These types are a little bit different. But know that here GLC mentions those types with ticks. So they're ticked. So it's just a specific way to say, well, we have different kind. We have not a data constructor, but we have a type here. So we can use it in our code either, but in general, if it's unambiguous, then we can use just F or just C and it works. So, well, it's type error. And if we attempt to ask for temp bool, and this was possible with phantom types, then it's not allowed here. So it says, well, we expect this kind temp unit, but bool has another kind, so we cannot use it. So this is a control that we have with data kinds. Data constructors become types, and we control them, and now any such behavior is prohibited. So very nice property here. Right? So all these examples. And of course, with data kinds, we can implement the same type class, same type instances, the same show instance. And as we saw, it works and everything just fine. All right. So with data kinds extension, we've got this ability to promote types to kinds, data constructors to type constructors. And now we've got more control at the level of types. So a very nice feature. More control is always good for Haskell. So type system becomes much richer with data kinds. And I'm going further. Type level literals. Let's look at this example and we start with the demonstration. It turns out that with these extensions, data kinds and no storage type, we can ask for the kind of numbers, numeric literals. So what's the kind of 42? Well, it's not. Not is a new kind which was introduced thanks to the data kinds extension. And of course, it has kind type. Type is type. And strings, string literals, they can also be considered as types. So this kind is called symbol. So we have not as type level natural numbers, and we have symbols as type level string literals. So it has type, kind type, and we also have lists at the level of types. So list, it's a kind constructor. So for example, this is a type here, and it has its kind. So kind is, well, it's a list of types. So we've got a bunch of whole things at the level of kinds. So now we can use all this stuff to implement, to control almost everything at the level of types. For example, we can control something like this. So this is classical examples, and I like it very much because it brings Haskell to some low-level programming when we can program something about operating systems and stuff like that. So here I have a very small example, and I want to keep pointers, aligned pointers in Haskell program. And I want to do some processing of those pointers. Let's look here. So I have phantom argument here. It's phantom type because, well, it's not used on the right-hand side. And with these phantom types, I can specify alignment for this pointer. And alignment will be natural number. So I want to encode this value of alignment. You may know that in memory, pointers can be aligned over every 4 byte, every 8 byte, every 32 bytes, etc., depending on the architecture we use, so on and so forth. So I want to encode this alignment right in type. And I also want to keep pointer value here as an integer. But it will be not a value, but it will be actually aligned value already. So we'll see how we set it. So 0 pointer is 0 pointer, and we can define 0 pointer for every alignment. So here we don't specify an alignment, just n. Remember, it's a for all n here. And we can write function over alignment. And here we have type system at work, actually. So we say that this increment function, it doesn't change an alignment. So we had a pointer aligned with this alignment, and it keeps it. So we cannot change an alignment of a pointer while using this variable. And then I add 1 here, but I mean that the actual pointer value is aligned, so it will be not +1, but it will be plus a line actually. How we can do that? Well, we can use this function for extracting actual pointer value. And this function is very small, but it's quite hot. And this function gives us first example when we go from the level of types to the level of values. So would there is a question in this chat, would there be an error for kind int 42? Well, yeah, I think yes, because int and 42, they have different kinds. So int has type kind type, and 42 has kind not, and we cannot have elements of list for different kinds. So yeah, this would be an error. Well, you know, kind checker works here also. Okay, so let's get back to the example. So we have this alignment and type, and thanks to the scope type variable, we can refer to this value in the body of the function. Okay, so we want to get actual pointer value here. And to compute it, we use the following function, not_val. So this function brings value from the level of type to the level of terms. It comes from the known not type class. Known not means a natural number, which is known at compile time. So that means that we cannot use it for some unknown at compile time alignment. But if we know that alignment when we compile this program, then we can refer to it, we can get that value, and look at this function from the standard library. It has proxy here, so proxy is still used, and it's not very old function, so it is used here. And it will be used, I think, forever. So we refer to this type, and then in the implementation for this particular alignment, we'll get this value, then we'll multiply it by p, and then we'll get actual value. Let's look at examples. So what's the pointer value for incremented 0 pointer, which was aligned by 4? You see, we have this information in type, pointer 4. Well, we have this information. So it's 0 pointer and then incremented. And we expect that the result will be 4. And it's really 4. Incremented by 1 0 pointer has a value of 4. Incremented of 1 0 pointer aligned by 8 bytes will be 8. So you see that we have the same expression at the level of types. We increment 0 pointer, but we are able to use this information from the level of type. So this is real type level programming. Well, very simple, extremely simple. But we use information from types to do something at the level of terms. So this is type level programming. We not only express an idea of alignment and type, but we also control it, and we also use it in implementation. So it works like that. And I have another function here, which is even more sophisticated, which allows us to get pointer value from any given integer. And whenever we work with such things like natural numbers at type level, it turns out that we quite often have to write or use functions like that. So at runtime, we are given with some value of, I don't know, well, for example, 8. It can be correct pointer aligned at 4 and 8, but it's not a correct pointer value aligned at 16 bytes border. So sometimes we can create properly aligned pointer, sometimes we cannot. So it depends on the actual value. But we don't know this value. You see this argument? It's usual term argument. So we don't know it's before we run actually this program. So we don't know in advance whether we'll be able to get just some pointer or get nothing. So that's why we have this maybe as a result. And we run this function and we ask for the natural value from this alignment. And we try to divide by it. And if the division is successful, we have a reminder of 0, then we return just. And if it is not properly aligned, then we return nothing. So quite often we have these functions. So, and this function takes some term level and tries to build properly aligned pointer controlled at the type level. So here we go the other way around, from the term level to the type level in some sense. So let's look how it works. So we try to create a pointer from 24, and it's successful. So we ask for a value, and it's just 24 because it is properly aligned. And if it's 42, and again, alignment is 8, it is not properly aligned. So we try to get pointer value, and we have nothing. Well, because there is no that value. Okay, so it was not properly aligned. So this is runtime. You see in GCI, we are running functions, we provide actual arguments, and at runtime, well, everything is controlled. Okay. So type level literals, I will skip, I don't have enough time, so I will skip to another example about strings, and I'll get to straight to the type families. Type families, or actually type synonym type families. And again, I have very, very simple example of a type family here, and I will run it in a demo. And of course, if you look in the internet for the examples of type family, you can see many, many sophisticated examples, but here is a very simple one. So what is type family? Type family is a simple way to express computations over types. Well, we have this type family simplify, and my idea is as follows. I want to turn every type to something simpler. For example, well, we want to translate our Haskell programs to some very primitive programming language with only 2 types, integers and strings. And as a first step of such a translation, I want to translate every type from one to another, from any Haskell type to integer or string. I define this type family. So it's like type signature for the type family, simplify T, where T is some type variable. And then I define several instances. For example, I want to convert integer to integer, int to integer, double and string, double also to integer, and several other types like string to string, char to string, bool to string. We can think about it as a pattern matching over types. We just define a function which operates over types and turns them to some other types. Let's look at it here. So we call these type families type synonym families because in some way we create a synonym for simplify int. So simplify int is an integer, is a synonym for integer type. Simplify double is also a synonym for integer type. Okay, so let's ask for the kind of simplify, and we see that it's a function over types, just as maybe was also such a function. So we define a function over types, and here we give its definition. And we can ask for the simplify bool, and it's a type. And we can also ask JSC to compute it. Look here, kind with this bank here, we ask to compute the simplify bool. And it can be computed, and we see here that the result is string. So bool is simplified to string. Okay. And yeah, now get back to the code, and let's try to write some function here. So now I want to use this type family to define something a little bit more interesting. So this is a function to simplify values, not types. So I have a type class, simplifier, with a function simplify, which takes any type t here, any value of type t here, and it turns it to the simplify t. So if we have double, then we should get integer as a result. If we have string, then we should get some string literal as a result. In order to define this function, we have to implement several instances. For example, we say how to translate integers. Well, it's just ID. And here we know that t is an integer and simplify integer is an integer. That's why this ID function type checks. In other integral types, we can use from integral. It's a function for converting from one to another, as you can see here. So if we have double, then we can do round, and then it will be rounded to an integer. If we have string, we can use ID because now it's a string. If it's a bool, we can use show. If it's a char, for example, we can build a singleton string from one char, single element string. And now we can use this function. Let's look here. So simplify for some double value is free. Simplify for true is true as a string literal. Simplify for x character is x string, and so on and so forth. So look, this function works over so different types, so different values, thanks to type family. So we've defined a family of functions, simplify, and a type family and a family of functions over term level. And now we can express one new thing, simplification, at the level of types and at the level of values. And look, this simplify type family and simplify functions, they are connected with each other. They follow each other. They work in a concert at the level of types and the level of terms. This is what can be done using type families in Haskell. There is also another sort of type synonym families, closed type families. See the difference here. Now I am doing widening. So I am trying to convert some type to something which is wider than this type. And it is closed, and it uses different declaration, different sort of declaration. And look, well, just different syntax type family where it is closed because we cannot write another line here, but thanks to the being closed, we can write something like that. So we say, well, we convert bool to integer, we convert int to integer, wide type. We convert char to string, and we convert any other type to string. This was not possible with type synonym families because everyone can add another type instance, or that they are open. But here with closed type families, we are not allowed to add anything. So that's why we can add this case which corresponds to everything. And once again, to use this type family, we have to define a type class with a function over terms now, and simple implementation for bools, simple implementation for integers, for chars, and for another type double. This will be used for the last case, wide and t. And now let's look how it works. So we use it with false, it's all right, and the result is int. So it was extended, bool was extended to widen to int. Character extended to strings. Integer numbers are extended to integers, int to integers. And the type is, of course, integer as a result. So another way to write a function which operates over so different types. You know that there are no simple connection between these types. Characters, bools, integers, but we can combine them into one interface, into one widen function using this type level functions. We just compute types from one to another using type families, and we have this result. Well, unfortunately, my time is getting over and over. So sorry, I will skip these 8 and 9 items. Yeah, by the way, of course, what I'm doing here, I'm just reading chapter 11 of Haskell in-depth book. So remember, Haskell in-depth book, and you can find every answer there. So I just feel sorry for skipping these items here, but well, I have no time for them. I will go straight to the item 10, generalized algebraic data types, and this will be simple one, latest one here. I will skip 11 either. All right, let's go to the generalized algebraic data types. And chapter 11. And this one. Okay. And demo. All right. Let's define this data type. My idea here is to give you a way to represent dynamic values in Haskell. You know that Haskell is statically typed language, and every value has its type, and we cannot just simply implement dynamic values of unknown types. So in order to do that, we have to use some sophisticated techniques. So for example, there is a module data dynamic, which implements full-blown dynamic types in Haskell. But here I'm trying to implement something very simple. And I will use this example to demonstrate generalized algebraic data types. All right, so this is a simple definition of generalized algebraic data types. So it is algebraic data types because we have several data constructors, S, C, and B, for respectively strings, characters, and bools. And what makes it generalized is this argument in the end. So the type is din value A. Think of it as if it's maybe A. But in maybe A, we have just a constructor and nothing constructor of type maybe A. And GADT, generalized algebraic data types, give us an ability to say din value string, din value char, din value bool. So this is GADT, an ability to replace type A with some specific type. And that's it. There is nothing more here. So we can ask for the types of these data constructors. The type of S is this one, C, this one, B, this one, from bool to din value bool. If you ask for the type of just, it will be A to maybe A. Type of nothing will be maybe A. So no particular type here. With the GADT, we can specify a particular type. And we can do something interesting here with this type. For example, we can define a function for getting value. So look here. So we have a value of type din value A, and we can extract A. We can also print this value. So let's look at this function. Print value here. So if we have B, we can print B. If we have C, if we have print C. And if we have S, we can print S. And there is one very important question which explains what is GADTs in disguise. You know that print requires having show instance. Why is it possible to use print B here at this point of program? Well, the answer is as follows. We have a value of type A. And you see that here in the type of print value, we have no constraints over type A. We have no show constraint. Nothing like that. So still, when we have B here, GHC knows for sure that B value in this case is a bool value. This means that generalized algebraic data types is technically B of type A, where A equals to bool. And this B equals to bool is a so-called local constraint which becomes available when we do pattern matching over this data constructor. So the moment when we try to use this B as a pattern matching, in a pattern matching, at this moment, GHC knows that the A equals to bool, and it can use whatever is available for bools. For example, show instance. And in this case, A equals to char, and GHC is able to use everything for chars. Okay, so with pattern matching over GADT constructors, we bring new local constraints. We don't have show constraint here for A, but we do have them here. And this is the only technical things about GADTs. So that's it. So GADT is an ability to specify this equality for this particular data constructor. Our type variable equals to some specific type, bool or character or string. So that's it. We can also put these values to type, to a list. For example, we can print these values here. We have two values like that, and we can print them, and it works. But if we can ask for the type, and the type is as follows, so it's a list of din value strings. But if we try to put different data constructors there? Well, it does not work because we have type error. Because these as hello and be true, they have different data types. The first one is din value string, and the second one is din value bool, and we are not allowed to put them in a list. So this is what we have in Haskell. So all the lists, they have should have the same type for every element. And to solve this problem, we want to wrap this value somehow. We cannot do it this way, because if you remember, in this function we have implicit for all, so we cannot say for all a din value a, because we don't know which a is it at this point. But what we can do, we can define another JDT which hides this value, this type variable somewhere inside it. So let's look here. So this data type is also JDT. We have wrap data constructor, and we have no type argument in the result. So this means that this type A is hidden inside. And once again, it is a JDT, and depending on the actual type here, we'll get a local constraint. It will be either bool or char, string, whatever, but it will be hidden inside wrapped data type. So now, this technique is very old, and I have a question about existentials in Haskell. And in fact, existential, we don't need existentials anymore. We have them forever in Haskell, but you may heard about exceptions type in Haskell. This syntax uses existential types, but it's actually the same thing as JDT. JDT is much more general, so we don't need existentials anymore in Haskell because we can implement the same thing with JDTs here. And it is implemented simpler because due to this idea of local constraints. And once we've wrapped everything into a type, we can put this value in a list, we can write functions over it. For example, this function tries to wrap a string. So look here, if the string is something which looks like bool value, like here, then we wrap it with b data constructor. If it's something that looks like false value, we wrap it with b false. If it's one character string, we wrap it with character. If it's otherwise, we wrap it with strings. Okay, so now we can take any string and wrap it. And once we wrap it, we can do anything with it. So once again, if we have a wrapped value, then we can do pattern matching over it. And once we have din value, and at this point, we will have particular type, and we can use it to run print value, and print value will pattern match over constructors of this dv value, and they will have either bool or character or whatever. And now let's look at examples. So here from string y we'll get true, from string x we'll get character, and from string hello we'll get string. So look here, so we've got a type for dynamic values, but then we wrapped it with a data constructor, and now we can work with it. And we can also create a list of wrapped values as follows. So we have strings, and then we wrap them with strings with wrapped values, and then we print them, and now it works. And it looks like we have different values of different types in a list, but technically they are the same. This will be a list of wrapped din values, and we can work with them as follows. All right. Let me finish at this point, and remember, you can use this promo code to get 40% degrees to get, well, I hope better explanations for all this stuff. So the whole chapter is devoted to all these things. And chapter 13, more about types, is even more interesting. I implement there some analog to the servant library, which is all about working with types. And then I use GADT there to implement another interesting thing, from I always wanted to implement verified version for elevators, verified software for elevators. And in chapter 13, you will see an example built around generalized algebraic data types, where I have correct implementation for operations over elevators. It's a very interesting chapter, so I hope it will be published soon and you will see it. All right, so thank you very much. Thank you for coming. Sorry for a long time of this stream. And I think it's over. So thank you and bye. Please buy my book, by the way. Haskell in Depth, tweet 40 as a promo, use it as a promo code. Okay, thank you. Bye.